Alrighty, hello and welcome to another Zosi session. How about that? Today is Thursday, if I'm not mistaken, and that means today, according to the skidoodle, we are continuing to develop our programming language built on top of stack-based virtual machine. Which we also developed ourselves. You can find the source code of this thing in the description. And yeah, today we're gonna try to do something very interesting. We've been developing this programming language for the past like month or so, and it can already do things, right? It can already have procedures, even though it doesn't, the procedures may not have arguments, right? It has global variables, doesn't have local variables, but we're gonna implement them later. If conditions, while loops, and even row pointers, and you can have an arbitrary access to the memory, and you have the whole memory in front of you. So the real question is this enough for the language to be Turing complete? Right. And another question, what is even Turing completeness? Right, so I don't know what is a Turing completeness. I'm not a computer scientist. But how I understand Turing completeness is basically the power of computational system, not in a sense of how much frequency in a CPU you have, or how many cores you have, or how many memory you have. Not that kind of power, but the power of computation in the sense that is it even possible in that computer, in principle, to do a particular thing? You know, you have a powerful game, and it can run on a modern computer, and it's gonna run fast. It's gonna run in, in 60 FPS, or what is the acceptable FPS these days? I don't play video games, I'm sorry, like 120, right? It runs in a very high FPS, and you try to run it on an older computer, right? And it runs in like 15 FPS, but it runs. So, in principle, that game works on that computer. That computer is capable of running that game, just slower. Right, so in terms of like computational power, I mean, is it in principle possible to do the same things as in other languages? Right, it may not be as convenient as in other languages, it's not gonna be as spready as in other language, but in principle, can I do the same thing in my language? So there's a pretty cool video by Ben Eater about Turing completeness. Ben Eater is a very cool YouTuber. I really recommend you to subscribe to him. He made a series about building 8-bit computer from scratch. Not that kind of Ben Eater. There we go. So and he talked about whether his computer is even Turing complete. Right. So for better understanding about Turing completeness from the practical point of view, I really recommend to watch this video. It's actually quite cool. So I'm gonna put it in the description, making a computer Turing complete. There we go. And also recommend to check out some of his other videos. The entire channel, his entire channel is actually super cool. I really recommend it. So, okay. So we need to somehow demonstrate that our language is Turing complete. And how do you usually demonstrate that a particular computational system is Turing complete or not? One way people usually do that, especially with programming languages, is that they implement some sort of like a Turing complete cellular automaton, right? So cellular, how do you spell it? Automaton, right? So yeah, and there's a lot of Turing complete cellular automata. So the automata is a plural one, automaton is a singular one, as far as I know. I don't know, it's this word is kind of weird. So one of the Turing complete cellular automatons is game of life, right? So, which means if we manage to implement game of life in our language, we can more or less safely claim that our language is Turing complete to some definition of Turing completeness, because to be Turing complete, you need like infinite amount of memory, and our computer doesn't have an infinite amount of memory, and but maybe we can build a computer that stops when it runs out of memory and waits until you add more. In that sense, it theoretically is going to be Turing complete. Yeah, my CS degree was a waste of time and money. Anyway, so But implementing the whole game of life could be quite tedious, given that our language is not really like, has a lot of convenience features. Is there an easier way to demonstrate that our language is Turing complete? And in fact, there is a simpler cellular automaton that we could try to implement in our language. It's called Rule 110. So Game of Life is a two-dimensional cellular automaton. Rule 110 is two-dimensional one. So it basically played on one-dimensional array. And like in Game of Life, each individual cell can be dead or alive, or 0 or 1. And what the game basically does, it scans the array in groups of 3. Right, and each group of 3 basically corresponds to a particular substitution pattern, right? So if this group of 3 matches this thing, it has to be replaced, the cell has to be replaced with this thing, right? So basically you have the state of the game, you have a lookup table, and you scan the state generating the next state, and you do that indefinitely. And that system, as far as I know, was proven to be Turing complete. Right. If we can implement Rule 110 in our language, we can demonstrate that it is in fact Turing complete. Right. So let me actually put this thing in here. So it's Rule 110. Rule 110. So maybe I'm going to also give you the link to Cellular Automaton, just in general. It's actually a very interesting article. I really recommend to check it out. Cellular Automaton. As a matter of fact, I remember that I did a series of streams where I implemented Cellular Automata. I think you can find that on my channel. So not in my language, but in general. Turing daily. Turing daily, there we go. Yeah, there we go. So there's like 5 streams were made on Cellular Automata. And yeah, do I even have a link to the source code? In any case, so here is this series on the topic. So streams, Turing streams on Cellular Automata. I think I spelled this thing correctly. So I think it starts with the video. Okay, so I'm gonna leave it as it is. By the way, I just remembered. Did you know that HTML5 and CSS3 is actually Turing complete? And as far as I know, it was demonstrated by implementing Rule 110 using only HTML5 and CSS3. You can encode Rule 110 in CSS3, so it's Turing complete, so as long as you consider an appropriate accompanying HTML and HTML file and user interaction to be part of the execution. Wow, that's actually very interesting. So, pretty good implementation is available. Alright, this version is outdated, newer here. Okay. Tab. Okay, so I can set the state. I assume that there is no JavaScript in here whatsoever. And what do I do now? I set the. Do you have to press something? I don't understand. I don't know. I don't understand how to use that thing, but okay. Oh, okay. This one at least works, right? This one at least works. Okay. Oh, I see what's going on in here. By the way, can I just set it like this? Oh, I see. So the orange ones, basically, whatever I have to like click or something. Yeah, that's really weird. Okay, in any case, I'm gonna, leave this thing in the description. So it's not the topic of today's stream, so whatever. Rule 110 in HTML5 plus CSS3. So our goal for today is going to be implementing this cellular automaton in our language. Let's go ahead and do that, I suppose. Let's go ahead and do that. So I'm gonna call it to BM, and I'm going to go into the examples, and let's create a file called rule110 bang. So we're gonna create an entry point, right? So, and what do I need to do in here? Let's actually just write hello world just to see if everything's still working correctly. Right. So it's gonna be no build. Example run, actually examples rule110 bang. Okay, so as you can see, it printed hello world. All right, so we need to define a special magical variable called Heap Base, and we're gonna call it. We're gonna assign a pointer, a type pointer to that variable. So, what is a heap base? Let's try to understand what is a heap base in our language. So let's imagine that you have a memory in here. So here's the memory. The memory starts somewhere here, right? So, and this is the address 0. So this is a memory of our virtual machine. This is not like the memory of the machine that we're running in, the actual one, right? So the language compiles to a bytecode of a virtual machine, and in the memory of the virtual machine starts with 0. Right, so you can define global variables in our language, right? So we can have something like A, B, and C, and all of these variables are basically appended. They're basically appended started from the 0, right? So basically, in the memory, you have a section that starts from 0, which contains all of the global variables that you defined. So here are all of the global variables. And at some point, global variables actually stop, and you have just free memory afterwards until, you know, infinity. It's not really infinity per se, but I mean, it's just like you can treat it as infinity. And heap base is a pointer that points at that specific point in memory. So that means after the heap base, you have a free memory that you can do whatever you want with, right? You can implement some sort of like a memory allocator and, you know, treat that memory as a heap, right? So, and this is what we're going to be using. This is where we're going to be allocating all of the necessary memory for our game, right? So I suppose we're going to start with the lookup table, right? So we have 8 values in the lookup table. So pattern 000 gets replaced with 0, 001 gets replaced with 1, and so on and so forth. You may notice a very interesting thing is that the pattern from right to left goes like a binary counting, right? So if you treat these bits as numbers in binary representation, they actually translate to numbers 0, 1, 2, 3, 4, 5, 6, and 7. So that means you can create an array of 8 elements, and in the corresponding indices of those arrays, you can store the replacement, right? So if you encounter pattern 011, right, you have to turn it into an index, right? So we need to calculate its index, and then you can quickly look it up and find the corresponding replacement. So we're going to treat the patterns as the indices in that specific table. Does it make sense? Hopefully that makes sense. So, and because of that, I'm gonna basically create a variable that points at the beginning of the table where we store that specific table, right? So, and of course it's gonna be a pointer. Maybe it would be actually quite good to also know the size of the table. So for that, we're gonna allocate a special variable as well. So unfortunately, we don't have arrays or initialization of the variables as we define them in a place where you define them. So that means we need to initialize all of that when we start the application, right? So the language is not finished yet, right? So we're gonna implement this kind of stuff a little bit later. Okay, so the table, I think we're gonna actually allocate the table after the variables. So let's actually put the table somewhere here. So this is where we're gonna put the table. So this is going to be the rest of the memory. It's going to be heap base. The size of the table, as already mentioned, is going to be 8. 1, 2, 3, 4, 5, 6, 7, 8. So we're going to have 8 elements in there. There we go. So, and now we need to initialize the elements of this table. So we're going to take 1 byte per element, right? We don't need more, right? Because we're effectively storing bits anyway. We could theoretically even store the entire table in a single byte because it's a... Well, that actually sounds like an interesting idea. You can compress the entire table in a single byte. And the pattern is determined by the position of the bit in that byte. I think it's like too much of a compression. It's totally unnecessary. So I don't think we're going to do that. All right. So we have a special way to actually dereference the pointers. Again, the language is not finished. We're going to have a special syntax for dereference the pointers a little bit later. So there we go. So this is going to be table. You know what? I want to actually call this a table base. Right. So we have a table base, and it's equal to heap base. Right. So the pointer that we want to dereference should point to the type U8. To learn more about this pointer syntax, you can watch the previous video where we implemented it. So I'm gonna leave the previous video in the description somewhere if I find my channel. For some reason, YouTube doesn't even recommend me my own channel. Maybe it's it's so bad it doesn't want to recommend me this channel. It's really strange. Yeah. So the previous video. In the previous video, we were adding the row pointers. Let me quickly put that in the description. Previous episode. In the previous episode, we were adding row pointers. All right. So, and in here, since it's the index 0, we need to store what? We need to store 0. Okay, so let's actually put it like this. So let's try to compile that and see what's going to happen. First of all, this thing has to be of the type U8 because we're trying to dereference the pointer as U8. So that means I need to cast this entire thing to U8. And everything seems to be working. Okay, so I need to initialize the next byte. So that means I need to take the table base and add 1. Right, and because of that, for the symmetry, I'm gonna actually add 0 in here, and in here we have to have 1. This is not gonna compile as well yet again because if you do plus on 2 types, they have to be the same types. Table base is a pointer type, and integer literals, they are I64 types, so you have to cast them explicitly. The language is a little bit strict on that part, but we're going to improve that a little bit later. In the future, I actually plan to implement some sort of a integer literal overloading. Essentially, the integers are not going to have any particular type until they try to interact with other integer types, and depending on what integer types they interact with, they're gonna basically turn into that specific type. It's not implicit conversion because there is no conversion between the type, because at the beginning integer literal doesn't have any type, right? It's just like the type of that integer is decided when it interacts with other things. It's kind of similar to Haskell's overloaded string, overloaded string literals. So essentially you have string literals, and you can define your custom string types that can be initialized with the string literals. So it's not really conversion per se, it's more of a it's more of an overloading of this thing. It's like similar to function overloading, right? The exact type is still decided at compile time. Okay, so if you want to learn more about this kind of thing, I'm going to put it in the description, of course. Haskell overloaded strings, right? There we go. This thing seems to be compiling, right? Cannot convert i64. Oh, okay, of course I have to convert it to pointer, otherwise I won't be able to add it to the pointer. All right, and everything seems to be compiling. So I need to do that 6 more times. 1, 2, 3, 4, 5, 6. And as far as I know, right, so I need to count them like this. 6, 7. All right, so where are the patterns? So 0, 1, 1, 1, okay, 0, 1, 1, 1, and the next one is 0, 1, 1, 0, 1, 1, 0. There we go. So I think we initialized the table successfully. So I think we're gonna actually initialize more things in the future, and it will be better to actually sort of tuck all of the initialization under some sort of a procedure. So let's actually quickly do that. So I'm gonna move everything into the init procedure, and in the main we're gonna just simply call init. All right, so everything seems to be compiling. The language compiles extremely fast. Look, look, look. I keep recompiling the whole language. So to recompile this entire example, it takes 16 milliseconds, right? 16 milliseconds to recompile this entire example. To parse it, to tokenize it, parse it, type check, and generate the bytecode, and so on and so forth. As far as I know, this command on top of that also runs it. Yeah, I think it also runs it. So if you put something like this in here, like hello world, yeah. This includes the startup of the virtual machine. Seriously. Anyway, so I want to see if I initialize the table correctly. So how can we do that? I want to print that table somehow. So let's create a special debug function which prints the table, right? Which prints the table. So right now the bytes of the table contain 0, 1, 0, 1, 1, 0 or whatever. So I'm thinking that I'm gonna iterate through these bytes and turn them into ASCII codes of corresponding digits. Then I take the table and treat it as the buffer, and I'm gonna give it to the right syscall, and it's gonna print that buffer in the standard output. So let's give it a try. That will destroy the table, but this is only for debug purposes, right? So I just want to print the table and see if it's initialized in the memory correctly. So to iterate the table, we need to create a variable, index variable. So let's call it I, and it's going to be I64. So we don't have for loops yet, so we have to use while loops instead. So less than table size. There we go. We have a table size. And we need to take table base plus cast pointer I, right? And this is the pointer of the single cell in the table. So maybe we're gonna have like an auxiliary variable that is called something like cell pointer, which is essentially the pointer. And this is where I'm gonna store that pointer for the convenience, right? So the next thing I want to do in here, I want to actually load the pointer, cell ptr, and maybe I'm going to have another convenience variable in here that actually stores this entire thing, right? So this is going to be cell, right? And I'm gonna store this thing back, store ptr u8 cell pointer, but then I'm going to take the cell and add the ASCII code of digit 0. So let me actually look up the ASCII code of the digit 0. 48. 48. Okay, cool. So we turned all of the numbers into the ASCII digits. So after that, I want to kind of add a new line after the table, right? So here's the table, and here I'm going to just put a new line like this, and I'm going to try to treat this as a string, and I'm going to try to print it. Okay, let's see what's going to happen. So cell pointer is going to be table base plus table size, but again we'll have to convert it to a pointer, right? And in here I'm going to try to store u8 cell ptr. So, and what's the new line? I think it's 10. I think it's literally 10. Right, there we go. So does it even compile? I think it compiles. Okay, cool. So after that, we just need to pass it to write PTR. So the pointer is table base and the size is table size plus 1, right? Because we also include the new line, right? And let's see what's gonna happen. Nothing happened because we never called this function. Okay, so let's do print table and let's go. And nothing happened. Guess why? Guess why? Because I forgot to increment I, right? So I also have to do I plus 1. There we go. And this is what we got. So this is what we have in the memory, in the table. Perfect. So we can actually do that probably maybe 2 times, right? So before we initialized everything and then after we initialized everything. Illegal memory access, that is very interesting. Oh, yeah, I see. Because the table base and table size are not initialized yet. Okay, so we can technically try to initialize them before init, but that doesn't make any sense. Well, at least we can see that. Before we had zeros and now we have like the actual table, but I'm not going to do that. So we're going to keep all of the initializations in the init function. All right, and again, we don't really need the print table because it's not really useful. It destroys everything essentially. All right, so we need memory to store the state of the game, right? So let's put something like state in here, right? So the state is going to go after the table. So this is layout of our memory. So at the beginning we have variables, then starts the heap base, and on the heap we store the table and then the state of the game. Right, so let's quickly do that. So we're gonna have something like state base and it's gonna be a pointer. So we also need to know the state size, right? So how many cells do we try to emulate in here? Okay, so state size, let's say that we're gonna have 30 cells that we're trying to emulate. So and a state base is basically starts at the end of the table, and the end of the table is table base plus table size. Right, there we go. So we also need to initialize the state base. So let's quickly do something like this. Store ptr u8 state state base, and we're gonna store something like cast u8 1. We're gonna store 1 in there. Is it gonna be enough? Probably. I don't know. Let's try to compile this entire thing. Oh, okay. This thing has to be converted into a pointer. All right, looks good. So now what we need to do, we need to organize this specific process, right? We need to basically scan the entire state with a window of 3 and constantly turn these 3 elements into an index in a lookup table and replace this thing in the next state. So here's an interesting thing. We probably should have a second buffer into which we calculate the next state. Because see, you cannot just take and replace the cells in the same buffer because it will alter the buffer and the consequent computations are not going to be correct. So I suppose it's kind of similar with how you implement Game of Life, right? In Game of Life, I usually have 2 buffers. In the first buffer, I have the current state of the game, and in the second buffer, I have the next state of the game, and I calculate the next from the previous one into the new one, and then I swap them around. As far as I know, there is like a way to do that without the second buffer, and maybe for the rule 1.0, there is a way to just store like a couple of the previous elements and constantly save them back into the same buffer. But I never done that, and it requires too much mental effort for me to come up with a good solution right now. Maybe we're going to do that later. So I think for now, I'm going to actually allocate 2 state buffers. How about that? So we're going to have state 0, right? So this is going to be state 0. And then after that, we're going to have state 1. Right, there we go. So, and essentially, we need some sort of a variable, something like state current, right? Current. that points at the current buffer, at the buffer where the current state is stored. Right, and when you compute the next state, the current is going to move the data into the next one, right? So it's going to move it to here, and then on the next state, this one is going to be the current one, and it's going to move it back, and so on and so forth. It's sort of going to circle the data between each other. Okay, so we need a special variable in here, something like var state current, and it's going to be I64. So maybe this one should be called states base because there are several of them. State current points at a single state, and state size is the size of a single state. Right, so states base is located in here, and in the states base we just store this thing in here. I also probably need to initialize state current, which is going to be equal to 0. All right, so but we also need to be able to display the current state, right? We need to be able to display the current state. So we can try to do a similar thing as we did with print table to debug things around. We can just convert each individual byte in here into ASCII code and treat this entire thing as the string. But the problem is we need additional byte for new line, and the states are really packed very close to each other, so we don't want to overflow them and just corrupt each other memory. So I think what we're gonna do is we're gonna allocate yet another buffer after the states, right? So and it's gonna be a display buffer, right? Display. Right, and the size of this buffer is going to be equal to the size of a single state plus 1 to accommodate the new line. Right, at the end of the display, you're going to have like a constant new line in here, right? So it's going to be always new line, and then you always will be able to just treat this entire display section as a string and constantly dump the current state of the game, right? So essentially a single computation, a single iteration of the simulation is going to be iterating through current state and computing the next state, right? So you're constantly iterating, computing the next state. And then to display the next state, you're going to iterate the state and put everything into the display buffer. And then you're going to take the display buffer and put it into the standard output. So this is how it's going to go, essentially. And what's interesting is that while computing the current state, you always look up the table, right? So you always look up the table. So the memory access kind of looks like this, essentially, right? So, and these tables are also going to be actually, you know, circling through each other because we're going to flip-flop in between them. All right. So, you know, before we implement the actual simulation, I think I want to implement a procedure that prints the current state. Print state current, right? So print state current. Emacs, what are you doing? What are you doing, Emacs? All right, so I need to start iterating the current state. So we're going to be iterating starting from 0 and up until state size, right? And at the end of the iteration, we are incrementing I. There we go. We are incrementing I. Okay, so I need to take the current cell. So the pointer to the current cell is located in states base plus state current multiplied by state size plus I, right? So basically with this, we're deciding which buffer we're currently printing, that one or that one, and I determines the offset within that current buffer. Right, so this gives us the current pointer that we want to work with. So it's going to be cell pointer. After that, we need to load the value from that cell pointer like this, and let's just store it in here. Okay, so I'm pretty sure it's not going to compile because, yeah, this entire thing has to be casted into the pointer, right? It has to be casted into the pointer, and there you go. All right, so now I need to take that cell and store it into the display buffer. So the pointer in the display buffer is going to be display base. I didn't allocate memory for the display base. Yes, I completely forgot about that. Let's actually allocate memory for the display base. So it's going to be located somewhere here. Display base is going to be equal to the state space plus state size multiplied by 2, because you have two state buffers, right? And this is where the display base is going to be, right? So yeah, so here we are initializing table, lookup table, then init state buffers, right? Two state buffers actually, and then here we have a display buffer. There we go. So yeah, after that, display base plus I think just plus I, right? And then we're storing U8 into the cell PTR as cell, but we need to convert it into a character, right? If cell is 0, right, it has to be, yeah, let's actually not use 0 and 1. Let's actually convert them to specific ASCII characters. So for instance, if the cell is dead, it's going to be space. If the cell is alive, it's going to be asterisk, right? So let's do something like this. If cell is less than 1, the thing we're going to be printing in here is going to be space. If I remember correctly, space is 32. We don't have a character literals yet. We're going to implement them later. Otherwise, we're going to have an asterisk. We're going to have an asterisk. Let me see what's going to be the asterisk. So it is 42. All right, looks good to me. So 32 and 42, cool. So I guess, yeah, we're printing the current state. That's nice. So if I try to print state current now, is it going to work? Okay, so it doesn't work in here because I probably have to do something like cast ptr, and here cell, oh yeah, this one is actually U8. Anything else? Yeah, I also have to cast all of that to U8. In the future, it's going to be a little bit easier to work with, but right now we're just trying to demonstrate that this entire thing is Turing complete. Okay, nothing happened because we prepared the display buffer, but we didn't even print anything. So let's try to do the following thing. I also need to append a new line at the end of the display buffer. So let me prepare cell PTR. It's going to be display base plus state size. All right, and in here we're going to store U8 cell PTR. New line is 10 as far as I know, right? So I think I remember that. All right, and after that I want to do write PTR display base, and the size is state size but +1 for the new line. There we go. Cool. So let's see if it's gonna work now. Okay, so it printed a single asterisk, and the rest of this thing is spaces, which is precisely how we initialize the first state. Right, so we can actually add more of these things. So this one has to be cast PTR 1. Maybe for the symmetry I'm gonna actually do something like cast PTR 0, and now the second one is, yeah, there we go, look at that. So the second one could be 0, but the third one could be 1. There we go. So as you can see, now we have this pattern in here. So, and if I switch the current buffer to 1, it's going to be all spaces, right? So in the second buffer, we have only all spaces. So I'm trying to print this buffer instead of the 0th one. All right. So that's pretty cool. I really like that. Okay, so the only thing we need to do is to implement a function that computes the next state, right? So it basically computes the next state. So I think I want to make a small break and make a cup of tea because I ran out of my tea. And after the small break, we're going to go ahead and implement this function. So yeah. All right. So let's implement next state function. So we know that the number of the current buffer is located in state current. But how do we know what's the state next? So let's actually allocate a special variable for the state next. There we go. So we have state current and we have state next. And the way we're going to compute this entire thing is going to be pretty straightforward. State next is going to be equal 1 to minus state current. There we go. So what that means? That means if state current is equal to 0, 1 minus 0 is going to be 1. There we go. So if the current is 0, next one is going to be 1. If the current is 1, 1 minus 1 is going to be 0, the next one is going to be 0. So basically we flip-flop between the numbers. So that's essentially what we have in here. Okay, let's start iterating the cells of the current state. So we're going to initialize I with 0, and while I is less than state size, right, we're going to be incrementing I like this. There we go. So first thing we need to do, we need to... Oh man, this one is actually very interesting. So the way you have to check the elements is the following. Right, so here is the state. Let me actually zoom in a little bit and... Oh, come on. So here is 3 elements. So this is the current state. And so on and so forth. And this is going to be the next state. There we go. So you're supposed to look at these 3 cells. I wish it was a little bit more convenient for me, so I think my hand is placed in a very unfortunate place. You look at these 3, and depending on what kind of pattern you have in there, you write a new value in sort of the middle one, right? Ignoring these 2. You see what I mean? The question is, what if the current, what if you start iterating from 0? So there is no left element, right? So there is no element in here. It is missing. So how should we handle this kind of situation? So there are several ways to handle this situation. So basically we can always interpret this thing as 0, right? So sort of clamp the pattern. So here's the first one, clamp. Clamp. I couldn't spell. Second one is wrap around. So if you try to access this thing, you in fact accessing the last element in here. So basically we are wrapping everything around. So wrap. And the third one is basically actually start from 1 and add and end with n-1. Right, essentially never try to calculate the pattern starting from here or here. Always like leave a little bit the room, a little bit of the room, so you always have 3 elements. We're gonna call it pad, right? So it's gonna be pad. I think padding is the easiest one to implement in here, so because for clamping you need to have like to handle like edge cases and whatnot. For wrapping around you need to deal with modular and stuff like that, and on top of that you need mathematically correct modular because you're gonna go like into minus, and minus should wrap around from the right side. So I think it would be just easier to pad. Essentially we need to iterate not from 0 up until n-1, right? But rather from 1 up until n-2, right? Something like this. That way we don't really have to worry about any of this kind of stuff. So let's actually do it like this. We're gonna start with 1, and we're gonna iterate up until state size -1. So we're gonna pad this thing like that. All right, so we need to start gathering the cell element. So cell pointer, states base plus state current multiplied by state size plus I. And all of that, of course, has to be casted to pointer. And there we go, we have a cell pointer. But we're only looking at the middle cell, right? So as I already said, we're basically handling triples, and this is the middle one, right? We're looking at the middle one. So maybe we need to start with the left one. So this one is going to be -1, right? And let's extract that cell. We're going to do load pointer u8 cell ptr, and there we go, we've got the cell. So we need to take all of these bits of the pattern and turn them into an index, right? So we need a special variable that will store the table index. So let's actually maybe create a variable in here, table index I64. And at the beginning of the iteration, we're going to take the table index and initialize it with 0. So this is a wrong function, by the way. This is a wrong function. Table index equal to 0. All right. So after that, what I need to do, I need to take a table index and assign it to table index multiplied by 2, right? So essentially I need to shift 1 bit to the left, but since I don't have a bit shift operation in my language yet, I can just multiply by 2. So yeah, essentially if you don't have a bit shift, you can always use multiplication. It's pretty much the same thing. Right, so multiply by 2 plus the value of the cell, and that's how I can add the bit into my index. Right. So essentially, okay, I can demonstrate you what exactly is going on in here. So index is initially 0. You have a pattern 1, 0, 1. Okay. So you see 1, you multiply your index by 2 and you add 1. The result is going to be 1. So now your index is equal to 1. Then you see a pattern 0. So you multiply by 2. And add 0, right? In that case, your pattern is going to be equal to 2 in decimal, but in binary is going to be equal to 10, right? So in binary. Then you take a look at the next one. So it's going to be 2 multiplied by 2 plus 1. So, and in decimal is going to be 4, 5, right? So it's going to be like that. But in binary is going to be 1, 0, 1. And there you go, we took this pattern, we turned it into an index, and now you can use this index in a lookup table to see what's going to be the next state of the cell. So that's precisely what we're doing in here. Okay, so it's going to be plus cell. Then I'm going to take the middle element and add it to the index, and then I'm going to take the right element and add it to the index. So I should not overflow anywhere in here because, as already mentioned, I'm iterating with the padding of 1 element from left and right. So let's see if this entire thing compiles, and it doesn't because, oh yeah, this entire thing has to be converted into U8. So maybe I should do something like this. It's going to be cast U8. Not quite sure because the index, right, index is I64, so that means we have to convert cell into I64. Okay, cast I64 like that. Cell is equal to the byte, but we need to convert it to I64 to be able to add this thing in here. Okay, so that makes sense. Okay, can it convert value of type U8? Oh yeah, we cannot do that yet. You know what, to be fair, do we really need table index to be I64? What if I make it U8? How many compilation errors I'm gonna have? Okay, so this one has to be cast U8. Our language is very, very strict, as you can see. Because of that, oh shit, that's actually pretty cool. So I don't have to convert this entire stuff anymore. Right, it's going to be cell, but a 2 has to be cast u8 2, and there we go, we have a table index. Perfect. Okay, this entire stuff compiles. Nice. So, and basically here we converted the pattern into an index, and we can now try to look up the corresponding replacement. So we need to do cell ptr, and we're going to be looking it up in the table. So it's going to be table base plus table index plus table index. Can I convert this thing straight into the pointer? I should be able to, I think, if I'm not mistaken. It is convertible apparently. Okay, so and then can I look up this thing, load ptr u8 cell ptr. So cell now should contain the replacement, and what's interesting is that we need to save that replacement into the next state. What's interesting is that the next state is basically the middle element of the current state, but with the current replaced with the next. So this is precisely where we need to store this entire thing. And now I'm gonna do store pointer u8 cell ptr cell. There we go. I think that's how you do that. So essentially we're iterating the current state. We're turning the triples of that state into an index. We're looking up the replacement in the table by that index, and we're putting that replacement into the next state, right? And after the entire iteration, we have to say something like state current is now equals state next. We're constantly flip-flopping these two buffers, and that should be it. I think that's pretty much it. Okay, so I forgot that we need to start from the state 0. There we go. So here is our initial state. Maybe I'm gonna actually set something like yeah, let's actually set it to the last element, because as far as I know, rule 110 grows from the right. Yeah. So as you can see in here, it usually grows from the right side to the left one. So what we can do in here is basically place some sort of a seed at state size -1 like this, right? So we're gonna have like a single seed at the right in here, right? And the pattern is supposed to grow to the left. Okay, so after that I want to do next state, right? Let's compute the next state. And it didn't crash or anything, which is already good. And can I now compute the next state? Okay, this is the next state, I suppose, right? So hopefully this is how we do that. I'm not sure. So, but maybe we have to actually set it not to -1, but rather to -2, because we're iterating with the padding. Oh yeah, now it looks a little bit better. Yeah. So we have a little bit of padding here. So yeah, now we have the next sort of state. So what if I do that several times? For example, 2 times. Okay, it seems to be growing. All right, this looks like the rule 110 pattern, the classical rule 110 pattern. Let's actually put that into some sort of a loop. Right, so we already have I. Maybe I'm going to introduce some sort of like a J. And let's just iterate a couple of times. So J is going to be initially 0, and while J is less than 10 times, 10 values, we're going to be iterating this entire thing like so, and it's going to be J plus 1, right? So we're going to have 10 iterations in here. Yeah, that's actually pretty cool. So it's going to keep growing. So can we do something like, I think it grows by 1 element per iteration. So if we make state size iteration, it will fill the whole thing, right? Yeah, there we go. It actually filled it a little bit faster than I expected. Oh yeah, because it has to be -2 because we have a padding. Yeah, there we go. So it actually filled it perfectly. So there we go. Rule 110 in our language. So we can try to increase the size of the state. Let's say that it's going to be 100, and let me actually demonstrate. Should display. There we go. Yeah. So, and it looked pretty much like this. Yeah. That's pretty cool. So yeah, our language is Turing complete, and here's the proof. Here's the proof that our language is in fact Turing complete, because rule 110 is a Turing complete system. I wonder if I can make it even bigger. How big can it get? Yeah. Okay, so that's pretty big, not gonna lie. It's pretty cool. It looks like a Sierpinski triangle or something, but it's like very uneven Sierpinski triangle. But yeah, it's doing things, which is kind of cool. Okay, let's actually set it to 30. Right, let's set it to 30. We can try to actually make it go indefinitely. Why not? So who said we can't do that? But I don't want to run it inside of the Emacs, because Emacs is a pretty slow terminal emulator. Fortunately or unfortunately, depends on how you look at it. So I'm gonna run it in a proper terminal emulator. TeamX is also a little bit slower than the usual thing, but anyway. So yeah, it goes indefinitely. So it just like repeats because it's clamped. It doesn't have any room to grow, so it just like repeats and blinks and stuff like that. So that kind of makes sense. So I think I'm gonna actually limit it to the amount, to the size of the state. All right, so because that kind of makes sense. And yeah, since this entire language compiles into our own bytecode, right? We can even take a look at the bytecode, something like debusm. So debusm, there we go. So here is the bytecode into which this entire thing compiles. Might as well actually put something like rule 110 busm and just open this thing in here. There we go. So this is the assembly of the bytecode of the virtual machine our program, our rule 110 program compiled to. And it's actually rather small, as you can see. So it doesn't have that much stuff. So 340 lines. And this is the entire memory that got initialized and whatnot. But of course, it actually consumes more memory than that, because it allocates more memory after after all of the variables. Here we only have the memory for the variables. So, and here's an interesting thing. In our infrastructure, we have code generators that take bytecode of our virtual machine and translate them to different native assemblies. Right, so we have translators for x86-64 and I think for ARM as well, and also for different operating systems like Windows and Linux and stuff like that. As a matter of fact, we can actually look them up. So if I run build toolchain bang, right, so here is the target. And if I take a look at target list, so here are all of the targets. So it's primarily x86-64 and ARM, right? And well, interesting enough, x86-64 is supported for 4 major platforms: Linux, FreeBSD, Windows, and macOS. So let's actually try to convert our rule 110 program into a native NASM for Linux x86-64 and see if it will work or not. Okay, so now here is the assembly that got generated from our bank problem for rule 110. So each group of instructions is a single bytecode instruction. Let me take a look. So that generated 335 instructions, like a virtual machine instructions. Okay, let's try to compile this entire thing into ELF object file. So we're going to do NASM f-elf64 or rule 110 asm, and there we go. We've got this thing. And now, can I link this entire stuff? I'm not sure if it linked it appropriately, but I'm gonna try to do that. Okay, let me try to do that one more time. And then I'm gonna just do rule 110. And there we go, we've got a file. We've got a file which is ELF64-bit least significant byte executable x86-64, statically linked, not stripped. And if we do LDD on that specific file, we'll see that it's not a dynamic executable. And let's try to run this entire thing. And there you go, rule 110, native rule 110 originally generated from our programming language. Pretty scuffed programming language, not gonna lie, but it is working programming language. It works and it can do things, and it's Turing complete. We demonstrated it just now. Right. We demonstrated that this language is Turing complete. Isn't that cool? Isn't that cool? I think it's pretty good fucking cool. God fucking damn it cool. I can't speak. That's how excited I am. I cannot speak. So let's commit that. I think it's pretty cool. So this is actually a pretty cool example. How would I implement such example if I had a better language? Well, I would definitely use arrays for tables and states and like display, but unfortunately we don't have arrays yet. So we're gonna work on arrays maybe tomorrow, right? We'll see. But I do have plans to add arrays with like different ranges and stuff like that. I have plans to add structures, enumerations. Definitely we're gonna have enumerations because enumerations is such a useful feature. We're gonna also add unions. What else I wanted to add? I don't quite remember, but yeah, we will definitely add all of the classical imperative programming like concepts and stuff like that. So, and we'll see how it goes. So let's commit all of that and let's think what else can we do in here. Since implementing rule 110 was relatively easy, maybe we can just go ahead and try to implement game of life, right? A game of life is pretty much like the same thing, but in 2 dimensions. Like here, we just need to take this example and add like a second dimension in here. Right, so maybe it's going to be difficult, maybe it's going to be easy. I don't know, we'll see. All right, so let's do rule 110. It's going to be branch. So what do we need in here? So I think I'm going to remove that stuff, and I'm also going to remove that stuff. So implement rule 110 in bang. I wonder if it's gonna spoil too much if I push that to the repo. I don't know if anyone actually follows that repo very closely. Nobody's watching it except me, so nobody's gonna notice that. Implement rule 110 in bang. All right, so, and 100 lines of code, exactly 100 lines of code. My God. Now that's the precision. Now that's the precision I'm talking about. Perfect. Okay. And while we're waiting for continuous integration, I think I'm going to make a small break. And after the small break, we're going to implement the game of life. Okay. All right. So I think CI is done. And let's just merge it. So, and fetch the latest stuff. Fetch the latest stuff. Let's go to the master, and there we go. Origin master. Okay, let's try to tackle something more complicated. For example, game of life. Let's go to the examples and let's do goal bang. So I'm gonna switch to a new mode. I'm not programming in Nim, by the way, but it's just like the keyword choice actually is perfect for Nim highlighting. I don't know why. And I also like to call this kind of things procedures rather than functions, and Nim seems to be the only language that supports this kind of stuff. We're going to implement our own Emacs mode later. So what I need to do, I need to yet again grab the heap base like this, and let's see what we'll need in here. Let me restart this entire thing. Right, we don't need that board anymore. So where the memory goes, so here's the memory, here is the memory, here we have vars, right? Yet again, this one is heap base. Heap base, and I suppose here we're gonna store the board, and again we're gonna have 2 boards, so this is gonna be board 0 and that one is gonna be board 1, board 1, something like this. Okay, so let's define something like board's base. It's gonna be pointer. So let me think. We also need the variables that determine the size of the board, right? So we need to have something like board rows, how many rows you have in a board and how many columns you have in a board. So this is quite important. After that, we also need to keep track of such thing as board current, right? And also maybe board next. This is very important. This is going to be very important. Do we need anything else for this kind of stuff? I don't think so. Maybe we'll need some sort of like temporary variables for like current row and current column when we're doing like loops and stuff like that, because we're gonna have nested loops and whatnot. So yeah, but I don't think it's needed right now. Anyway, let's actually define the init procedure and initialize everything there. So board space is going to start at heap base. The board rows, the amount of rows we're going to have in there is going to be 10. So we're going to have for now 10 by 10 board within which the game of life is going to be played. So the current board is going to be 0, right? The current board is going to be 0, and the next, it doesn't matter, is going to be like reassigned on each like next state and whatnot. Right, it would be also kind of nice to assign some pattern within the current board, just to be able to see it. But we won't be able to see it unless we have a way to print the current board, if you know what I mean. So we need something like proc print board current, right? So print board current, and let's just call this function after all of the initialization. So how are we going to be printing all of that? I think we should print all of that row by row. Yes, we need to print all of that row by row. So we'll need to add a similar display buffer as we did in a rule 110. Display, right, and the size of the display buffer, the size is the size of the row, like yeah, basically columns. The size of a single row is the amount of columns, right? Here is the rows, here is the columns. The size of a single row, the size of the single row is the amount of columns, right? Makes sense, makes sense. Okay, and the size of a display is going to be amount of columns because it's the size of a single row, plus 1 to accommodate the new line. Right, and essentially how we're going to print the current board, we're going to be iterating it row by row, and each row is going to be translated into the display buffer, and at the end of the row iteration we're going to be dumping that display buffer into the standard output. So we're going to be printing it row by row, right? So that's going to be the idea, at least. We'll see how it goes. We'll see how it goes. So maybe I'm also going to allocate special variables like cell and cell pointer rather, and the cell, because they're rather convenient. And let's see how it goes. Let's see how it goes. We need to start iteration. Don't say it. Don't say it. Don't say it. Of our nation. So row 0, and while row is less than board rows, we're going to be incrementing the rows. There we go. We're iterating row by row. Next thing we need to do, we need to iterate column by column. Board columns. It would be way easier if we had for loops, but unfortunately we don't have for loops yet. I'm not against for loops, it's just like I need to spend time implementing them. Right. Okay, so we're iterating row by row and then column by column. Now, I need to identify now the position of the cell that I need to grab and put into the display buffer. And I forgot to allocate the display buffer. I talked about display buffer and I forgot to allocate it yet again. Okay, so what we need in here is a special variable display base pointer, right? So display base is located at board base plus the size of a single board. The size of a single board is board rows multiplied by board columns. right? Multiplied by 2 because you have 2 boards, right? You have 2 of them. And this is where the display buffer starts, and the size of the display buffer is the size of a single row, basically columns, plus 1 for the new line. Make sense? Hopefully makes sense. Cool. Now, let's determine the position of this cell. So what I need to do in here, I need to do board base plus board rows, board calls. And I feel like I'm going to be using this pattern, board rows multiplied by the board calls, way too many times. So maybe it would make sense for me to introduce a variable, board size, I64. And it's going to be equal to simply rows multiplied by columns, right? And that way I can quite easily just refer to board size. We don't have compile time constants or anything like that, so that's why I have to like actually allocate memory for these kind of things. Like in a real production language, this would be completely unacceptable, but in our case, I mean, yeah, our goal right now is not to be production ready. We're just trying to demonstrate that this entire thing is at least Turing complete. We already demonstrated it, so we're just trying to push it a little bit further from rule 110 to 2 dimensions of you know, game of life. All right, so here we're going to have something like board size multiplied by board current, right? There we go. So we determine the position of the current board. So within that board, we need to offset everything the following way. Row multiplied by the board columns, right? Plus the column, right? This is quite interesting. So first we determine the start position of all of the boards. Then depending on what is the current board, we're gonna add or not add board size. And then within the single board, we are locating the row. And then within the single row, we're locating the cell. Right, so, and that's how we calculate that position in here. And here it is, here is the pointer to the cell that we need to extract from the current board. So, and the way we're going to extract it is by load ptr u8 from cell pointer. Right, so we're using pointer arithmetics in here. And this is not going to compile, by the way, because we need to do a bunch of conversions in here because our language is very strict about the types. So where is the... Can I just do deposit though? Yeah, there we go. Board base, boards base. Okay. And this one has to be casted to pointer, as far as you can tell. So could not, yeah, boards base. And this one is going to be cast pointer to this one. There we go, it worked. So yeah, it generated the assembly of this entire thing. Cool. So here we got cell. Now we need to put that cell into the display buffer, right? So it's going to be cell ptr, display base plus the column, as far as I can tell, right? Because we're iterating like columns right now. And what I'm doing in here, if cell is less than 1, right? If it's less than 1, that means I store into the display buffer, U8 of course, space, and space is 32, right? Otherwise I need to store asterisk, and as far as I can remember, asterisk is 42, so 32 and 42. Cool. Yeah, I guess that's it. So after I filled up the row of the display buffer, what I need to do, I need to add a new line. So it's going to be display base plus cast ptr board columns, right? So it's a very end of this thing. And I store ptr u8 cell ptr, and what I'm going to be storing there is 10, which is the new line, and then I do write ptr display base, and the size is board columns plus 1 to take into account the new line. Okay, so I guess that is it. Is it gonna compile? It does not compile because I is I64. We need to convert it to U8. Expected. Okay, this is another classic thing. All right. Okay, so it compiled. Right, that's cool. So we should be able to print the current board. So right now the board is not initialized with anything, so it should basically print 10 by 10 amount of spaces, if I understand correctly. Right, so let's try to run this entire thing. Well, it's not going to even print anything because we're not even calling the print board current. Oh, we do call it. Okay, so that's fine. All right, so let's do run, and I think I forgot to do something very, very important. Yes, I forgot to increment column. Right, so I forgot to do column +1. There we go. And yeah, as you can see, it did the thing. I think it did the thing. So if I query replace space with dot, yep. So in terms of the characters, how many characters do we have in here? We have 10 characters. And how many lines do we have in here? We have 10 lines. So we got 10 by 10 spaces, essentially. That's what we've got. So it works at least precisely as you would expect it to work. So one of the things we can do, we can try to put something into the board, into the first board. So how are we going to do that? Store ptr u8 boards base, and in that place we can just put 1, right, and that will result in a single live cell in the left top corner, right? So this is what it's going to result into, and there we go. Here it is. Here it fucking is. Here it fucking is. So, but the thing I want to do, I want to actually put a glider there, right? I want to put a glider there. But to put a glider there, we need to figure out the coordinates of the glider. So let's actually quickly do that. Yep. So that should be enough. 0, 1, 2. And then we're gonna have, yeah, 0, 1, 2. So the glider is basically this, right? This is the glider. So you need 5 alive cells. The first cell is 0, 1. So first is the row and the second is the column. 0, 1, 1, 2. Here's the 1, 2. 2, 2, 2, 2, 2, 1, and 2, 0. There we go. So we just need to set these cells alive somehow. We'll see how. Cheers, by the way. 0, 1. Okay, board base plus I suppose board calls multiplied by row, right, in our case row is 0, plus column, right, and this entire thing has to be casted to pointer, right, and there we go. So here is the row and here is the column, right, if I understand correctly. So let's see if it's gonna work. Yeah, it actually shifted it to here. Okay, fair enough. 1, 2, 1, 2, 2, 2, 2, 2, 2, 1, 2, 0. There we go. And there we go. We've got a glider. Look at that. We got a glider. Nice. So I suppose the next step now is to make that glider move. Right, we just need to make it move. If I actually switch the current board to 1, it will display nothing because there is nothing on the second board, but there is something on the first board. Okay, that makes sense. Okay, so let's introduce the function next board. Next board. And we're gonna print the value of the next board. Maybe it would be nice to somehow separate those things, right? So there's the first board and then there's the second one. So should be all right. So for now, I'm gonna do debusm, so it doesn't start executing things. And here is the line that we're trying to print here. Yeah, really like that. And still, we don't really have that many instructions though. So it's pretty concise, pretty concise. Okay, so let's start the iteration. Row 0 while row is less than board rows. There we go. And here we're going to increment rows by 1. While columns is less than board columns, we're going to be incrementing columns plus 1. There we go. Cool. So I suppose the next thing we need to know is the amount of neighbors. I usually calculate the amount of neighbors as a separate functions, but right now our procedures are incapable of accepting any parameters or returning any values, right? They're literally just reusable pieces of codes that you can call to. So we're going to implement all of that a little bit later. What we need to do in here, I think we're going to inline the computation of amount of neighbors. So that means we need to be able to compute the amount of neighbors into some sort of a variable. So let's actually call this, like define this variable neighbors. Also, I think I'm going to move maybe, I don't know if it makes sense to move it anywhere. Okay, let's not gonna move. I'm not gonna move that. So neighbors initially is 0. So how are we gonna be iterating through all of the neighbors? Right, I'm gonna use my usual trick, right, where I'm essentially iterating the quad, right? So look, I have this cell, right? So here is the cell. And I need to go through each and individual neighbor of that cell. So the usual trick I do is basically I go one cell by diagonal to here, and I just iterate with like a two-dimensional loop, with the nested loop, a square of 3 by 3. Right? I'm just iterating the square 3 by 3, ignoring the central piece. And that way, I'm essentially iterating all of the neighbors of that central piece. So that's how I usually do that. Believe it or not. Believe it or not. And I think we're gonna start, yeah. We're gonna have problems in here because, yeah, I need to be able to iterate from -1. And this one is gonna be kind of painful. Shit. We'll see how it goes. So as far as I know, I64 is negative, so it should be all right. Should be negative. Shouldn't create any problems, but I'm a little bit worried. I'm still a little bit worried. So let me try the following thing. I'm gonna just check something. So it's gonna be full bang proc main. So it's gonna be new. And in here, I'm gonna create a variable var I64, and this one, we don't have a negative numbers yet. So to have negative numbers, we have unary minus, but we don't have that. We only have binary minus, so we can actually do something like this, right? If you want to define -1, you just do 0 - 1, right? And that should compile, as far as I know. Okay, I'm not saying that my language is good, okay? I'm saying that it's Turing complete, right? So we're gonna make the language good a little bit later, all right? So let's just try to run, or maybe at least debusm the full bang, and this is what we've gotten here, right? So we push 0, 0, then minus I, and then I write it into this specific memory. Okay, that looks okay. So, and while I is less than 1, right? Actually, less maybe or equal. Do I even have less or equal? Maybe I don't even need to, because I can do something like 2. I'm gonna do right star, and then I'm gonna do I plus 1. So what I'm trying to see is whether it's gonna print 3 stars, right? It should print 3 stars. Do I want to put a new line in here? Maybe I do. And yeah, it printed. So basically, can I iterate starting from the negative numbers? Because I never actually checked that, so I wasn't 100% sure if it's gonna work the way I would expect it to work. Right. All right. So let me see. Let me see. So what I want to have additional variables for iterating rows and columns. So maybe this one is going to be called something like drow I64, right? And that one is going to be called dcolumn I64. Cool. And as we calculate the neighbors, I'm going to initialize drow with row -1. That's quite important. And we're going to do all of that while row is less than row +2. Right. And the way we're going to do that is drow equal drow +1. There we go. So we're trying to iterate all of the neighbors. Then we're going to have dcolumn. It's going to be column -1 yet again. And while dcolumn is less than column +2, we're going to dcolumn. We're going to be incrementing dcolumn +1. There we go. Cool. So here we're computing neighbors. All right, maybe I'm going to actually put something like this. Neighbors begin, and this one is going to be neighbors end, because it's quite a huge of a process. All right, and now we need to ignore a very specific value, right? If drow not equal, we don't have not equal. My God, I'm trying to avoid adding new things into the language, but I think it's like, yeah, at this point it's unavoidable. We need to have something like not equals. Do we even have equals? I don't even remember what we have. Okay, not equals row, right? If it's not equals to row. And yeah, so we also don't have and. Dcolumn not equal to column, right? And maybe we also want to add something like and drow is greater or equal than 0 and drow is less than board's row. So that's also quite important because you need to like boundary check. Only then we're going to try to use all of that. But we don't even have any of the separators. But they should be relatively easy to add, actually. They should be relatively easy to add. So let me see what we can do in here. So maybe first thing I want to do is check the boundaries, right? So the first one is going to be drow greater than 0 and drow less than board's row, right? There we go. So we have that. So and the next thing is if dcolumn is greater than 0 and dcolumn is less than board's columns. All right, like this, board columns. So we checked another thing in here. So and if drow not equal row and dcolumn not equal column, right? Only then we are extracting the cell. Yeah, we have to figure out the position of that cell as well. So the position of that cell could be probably taken from somewhere here, right? So this is how we're going to compute all of this. But I also forgot that we need to compute the next board. So let's actually quickly compute that. So it's going to be board next is equal to 1 minus board current. It's the same situation as in rule 110. This feels like rule 110, but with the second dimension. So it's pretty much the same structure in here even. Yeah, it's pretty much the same structure, it's just like, yeah, 2 dimensions. Here we have board size, board current, and the column is dcolumn. Actually, board columns D row, here's the D row, and here's D column, and you have a cell pointer, and then you can extract the cell. Load pointer, U8, cell pointer, and there you go, you've got a cell. And if the cell is greater or equal, so we already have a greater or equal, that means I can just use it. I'm going to simply increment the neighbors, so it's going to be neighbors plus 1. There we go. Was it worth it? I don't know, probably not. But I tried. None of that is going to compile, by the way, because we don't have these separators. We have a less separator, we don't have greater or equals, we don't have and, not equals, but it should be relatively easy to add them all. So we'll see how it goes. So let me try to compile this entire stuff. Okay. So it's going to be debusm goal, and there we go. We don't have such a token at all. Unknown token starts with this kind of thing. Okay, so I think I'll need a cup of tea for that, right? Because I'll have to go into the compiler and just like add the additional operators. Luckily, we have the pretty good infrastructure where you can just add a new operator, go through the compilation errors, and you will have a new operator without even thinking about it. So it should be relatively easy to pile more and more operators in our language. So, but I'll definitely need some caffeine for that. So let's make a small break. Okay, so we need to add like 3 new operators or something. So the first operator I think is greater or equal, the second one is and the third one is not equals. Yeah, let me actually do something like this. And not equals. Okay, so let's go to the parser. I think this is where it's located, binary, yeah, there we go. Here they are. Here are the kinds of the operators that you can have. Kind greater or equal. So it's going to be GE, greater equals. So we also have less. I feel like I want to call it LT, less than, right? I think it makes more sense. Greater equals, then it's going to be and another one is going to be not equals. Okay, so we renamed 1 binary operator and we added 3 of them. So that should cause a chain of compilation errors, and let's actually go through all of them and fix them. And at the end, we should have 3 new operators that we can use in our program, hopefully. We'll see how it goes. So let's rebuild everything, no build test. This is not how we do that. There we go. All right, so what do we got? We have LT. All right, so now it is called LT. Maybe because of that. So this is a table, basically correspondence between the type and the binary operators, right? So whether a particular binary operator is applied to a particular type. So here I actually renamed less to LT. So let me actually quickly replace all of that, and that screwed up the this thing. So I wonder if I can quickly fix all of that. I'm not sure. Let me try that. So query, and not query replace, but align equal dot. Okay, it worked. It actually worked better than I expected. Nice. Okay. So here, this is what happened. We introduced a couple of operators, so we need to add those operators to the types. So I'm going to go to the parser, and here are the operators. So will void have any of these operators? I don't think so, to be fair, right? So we're gonna mark them as non-existing for the void. So it's going to be something like this. Might as well actually just copy paste it like this. There we go. So they do not exist. So what about the I64? I think for I64 they should exist. And let's do it like this. It's going to be true. And first thing, what kind of instructions should we use for greater? Okay, so I think, yeah, for greater or equal, we have to use greater equal integer instruction, the famous gay instruction. So, and the result of greater equal has to be bang type boolean, right? When you do comparison, you get the boolean. So the and should use this one is interesting. So and is not really applicable for the integer right now. So I think this one does not exist for the integer, right? So it's only applicable for the booleans. Not equal is rather interesting. So I think, do we have something like nay? I think we should have something like that. And the final result is going to be bang type boolean. There we go. All right, so let me actually try to compile this entire thing and see. Okay, so it didn't really complain about this part, so that means we do have nay instruction, right? Yeah, we do have nay instruction. Okay, so what about for U8? For U8, well, U8 is unsigned, so we cannot use gay. We have to use gayu. I think greater equal unsigned, and similarly an unsigned version of not. And you can do and on that. All right. For the boolean though, I think we're not gonna have this instruction for the boolean. Greater equal is not exist. This one should also not exist for now, even though it probably makes sense to have not equals for the boolean, but I'm not going to introduce it. The only instruction we're going to have in here is probably and. And instruction for this thing is going to be and, just and, but I don't remember, is it and b or not and b or something else? I need to take a look at my table where I have different instructions. Instruction and, so there's the and b. So it's actually and b. I think we don't have a boolean and, right? We only have like a bit and. Really? Let's actually not introduce and. I don't think we can actually live without and for now. But yeah, I don't think it's gonna exist for now. It's kind of weird. I don't think we have instructions for this entire thing. So, and because of that, we'll have to go back to our program, right, and actually split those things into separate ifs. It's gonna be kind of weird, but I mean, you can do that, right, and that sort of kind of like eliminates the need for ands, right, and that means we'll have to add less instructions at the end, right. So we have that, yep. Very equal, if that, and let's also split it like this. So this one goes away. Oh my god, Emacs is so annoying. It's not really Emacs that is annoying, but rather a nim mod that I'm using for this stuff. Okay, and if this one. Again, I'm not trying to demonstrate that the language is good or pretty or anything. I'm just trying to demonstrate that it's Turing complete. Even though I already kind of demonstrated it, but I mean, I'm trying to demonstrate what I can implement game of life in it. All right, so yeah, in the future I'm gonna add and. It's just like, it's not clear how to add it right now, so it's gonna be a little bit easier to just have a bunch of ifs in here. All right, so let me see what we've got. So we don't have and. Let's find another and another and another one. Forgot to save everything. Okay. So they don't exist for boolean. For the pointer though, I think we're gonna use the same as for the unsigned things, because pointer is basically unsigned integer. And yeah. All right, so we added 2. That means this becomes 6. All right, so I think we associated all of the binary operators with their corresponding types appropriately, more or less, hopefully, and let's continue the compilation. Okay, so now we need to define, we need to associate the binary operators with their corresponding tokens and precedence. Right, so it has to be some sort of a precedence. Also, I want to rename this token. Right, let me actually go and rename this token. I wonder where I can find it. Okay, so this is less. I think I want to call it LT. And this one also going to become LT. So what kind of operators did we add in here? Bang, binary, OP, LT. Actually, not LT, but GE and not equal, right? So GE and not equal. So the associated kind is GE. The token is going to be GE token, and precedence is rather interesting. I think the precedence is going to be equal to the same as LT, right? Because they're comparison operators, so they have to have like the lowest possible precedence, and because of that, I'm going to actually put them together. Right, I guess that makes sense. At least it makes sense to me. So this one NE, and also it's going to have the lowest precedence possible. So plus and minus have a higher precedence, and multiplication has a higher precedence than plus and minus. So this is how it goes essentially. All right. Do we need anything else? Okay. So this one is called LT. And maybe I also need to add the new operators in here, greater equal, so it's going to be GE, greater equal, and not equal. So a not equal is this, essentially. And I added 2 of them, so that means it's going to be 17 now. Okay, so what's wrong in here? Oh yeah, we don't have those tokens yet. Okay, so that means I need to go to the Lexa and basically add them. So we're gonna have GE and NE, right? So so this one is LT. What is that actually? Token kinds, and we also need to do something like GE greater or equal and not equal. Something like this. Why all of that is not properly aligned? Now we're talking. So when we added 2 of them, so now we have 17 of them. All right. Anything else? Okay. So if we added hard-coded tokens, we don't have to do anything in here, so it's nothing special. All right. So what about this one? Oh yeah, I associated tokens appropriately, hopefully. So that means I added 2 of them, so this becomes 6. All right, anything else I need to do? So this one is LT, and since I added 2 of them, I also need to add them here, because none of the expressions starts with these tokens. So in that case, we have to like throw this error in here. Okay. So this is LT. This is about the statement, right? So we're checking for the statement. Yeah. GE and E. Anything else? And okay, so we just added 2 new operators. Yes. So the code base is organized so you add a bunch of enumerations and you just follow the compilation errors, and then at the end of this process you're going to have 2 new operators, hopefully. So let me take a look at the example in here. So the example is absolutely ugly, I do realize that, but the language is not finished yet. So I'm trying to do what I can with what I have. Right, I just trying to see if I can even implement a game of life in this language. I think it should be doable. I do think so. So let me double check the compilation table one more time, because I'm a little bit scared that maybe I did something wrong here. Greater, yeah. Well, I mean, yeah, there's nothing much we can do in here, so that all of that makes sense. I'm not sure why don't I have and as like for booleans, why do I have only binary AND? Binary AND may not work, right? It may not work because you may have two numbers that are greater than 0, but they cancel each other out if you try to do AND on them. So we'll probably have to extend the virtual machine at some point. We'll see how it will go. All right, so let me try to compile the example. So I'm going to try to debug some goal and greater or equal. Oh yeah, okay, so it managed to parse this thing because this is a compilation error, not a parsing error. Okay, so this one has to be something like cast U8, and yeah, it worked. So as you can see, I just added two new operators and it just works. It now understands all of that. So we have a pretty good code base that allows you to just pile more and more operators on top of the language. So yeah. Which is quite important because you don't really know upfront how many things you need. So it's better to implement very minimal language and start developing it, and then see what you need to end and just add things on top. So we didn't work with AND because apparently we have a flow in the virtual machine. So virtual machine doesn't know how to do AND in a Boolean sense, right? It can only do AND in terms of like bits. But maybe... usually if we do comparison, we end up with just 1 or 0, which is usually enough for conjunction. So maybe I'm gonna just add AND. I'm gonna add AND and then put it to do to actually revisit this entire thing. Okay, let's actually quickly add AND. Before I do that, let me do a committee. Add greater or equal and not equal operators to the language. To the language. And I'm gonna push that right into the repo. Do I really want to edit right now? Nah. Okay, whatever. I'm gonna edit later. Too lazy right now, I'm sorry. Okay, so everything seems to be compiling. So let me double check everything. So I'm starting to iterate from -1 up until that one, and then columns from minus column up until that one. If d row is greater than 0 and d row is, I would actually like to, no, it's fine. Greater than 0 and less than that, and d column greater than 0 and less than that, and d row not equal row, and this one is not equal that. So actually we have to have OR between them, right? Because, yeah, we need OR in here. Fuck. So essentially it has to be something like yikes. Okay, so I guess we'll have to add them. If I'm gonna add row, by the way, I might as well add AND too. Why not? Right, I might as well add 2. Emacs, this mode is hella annoying, and this is because nobody uses it, right? All the Nemers, I'm pretty sure they're using Visual Studio Code or some other Zoomer stuff. Okay, so this one is here, so that means I need to remove it from here. All right, so and this one is going to be something like this. Yeah, we do need to add AND. So this is so annoying. Okay. I absolutely hate it. Okay, so yeah, if we're gonna add OR, and we'll need to add OR, we might as well add AND. Okay, so let's actually go ahead and do that. Why not? I wonder if I'm gonna screw it up really badly. I hope not. All right, so parser, we're gonna start with the parser, and we're gonna straight up add a couple of things in here. It's gonna be AND and OR. There we go. So now we have 2 kinds of operators, and probably because of that we'll have to have like a new precedence in there. We'll see how it goes. Okay, so let's go. It's gonna be test. What do we got? Okay, so what's we're gonna have in terms of or and end? And or are not applicable to void, so we're not gonna do that. What about I64? Let's say they're not applicable, and I forgot to put false in here. None of these decisions are final. Everything may change at any point. Okay, so maybe we're gonna have and or for I64 for bitwise operations. We don't know yet, so nothing is finished. The language is not finished. Okay, nice. So what about U8? I think for U8 it's also going to be false. We're only going to add that for the booleans, right? I think it makes sense to add it only for the booleans for now, because we want to separate like bit and boolean and. Right. So what's going to be the instruction in here? I suppose the instruction is going to be pretty simple. It's going to be instruction and B, and this one is going to be or B, and the return result is going to be bang type boolean, right? So it's going to be bang type boolean. All right, bang type boolean. For the pointers, we're probably not going to have that. Yeah, there we go. So we populated this table. So we added 2 operations in here, so it's going to be 8. There we go. So that's going to be the next one. All right, so here is the definition. This one is interesting. So the lowest precedence right now belongs to comparison operators. Right, but I think the and or, Boolean and or, should have even lower precedence, right? So comparison should have a higher precedence than the conjunction and disjunction. So that means we'll have to increment or offset this precedence a little bit. We'll see how it goes. So I'm going to start with and, right, and the kind here is and, the token is going to be and the precedence is going to be 0. Because of that, everything that has the 0 precedence has to have precedence equal to 1. Right. Now everything that has the precedence 1 should have the precedence 2, and everything that has precedence 2 have to have a precedence 3. Right, and we don't have a third precedence, but the compiler will warn us about that, and we're going to add it a little bit later. Okay, so we have and or, right, or is going to be like this. I'm going to just make them have the same precedence for now. And we'll see how it goes, right? Because from a mathematical point of view, or sort of corresponds to like plus operation, and corresponds to multiply operation, and you may want to and you want and to have like high precedence from the mathematical point of view, but this is not like a mathematical language; it's a programming language. So we'll see how it goes. None of that is final, all right? So we don't have this kind of token, so let's go to the Lexa, and we need to add a couple of these things. So it's going to be and or. We'll see how it goes. So we have a bunch of tokens in here, so let me quickly add them. And token is going to be just at. And or token is going to be just like this. Okay, so we added 2 of them, it's going to be 19. Might as well also add this thing right away in here. So it's going to be and, or, this is needed for the names and stuff like that. So and, or, and now we have 19 hard-coded tokens, or generally tokens. Okay, there we go. What else do we have in here? We edit only hard-coded tokens, so there's nothing needs to be changed in here. Okay, so we don't have a precedence 3, so let's actually add it. Yep, it's going to be equal to 3. 0, 1, 2, 3, and then we have like a maximum amount of precedence. Do we have anything else? So, oh yeah, I forgot to increment it. So we added 2 of them, that means it has to be 8. I think, yeah, I think everything is edited correctly here, more or less, hopefully. Okay, so what do we have in here? Oh yeah, so now it's parsing. I suppose none of them start with none of the expression will start with and or for now, so that should be totally fine. And another one is pretty much the same situation, right? And or, none of them start with any of this stuff. Okay, looks good to me, I suppose. So let me see. So now we should have two new operators. So that required a bit of changes, but yeah, that was relatively straightforward. So that thing should work now, hopefully. Okay, so let me try to run this entire thing and just see if it compiles at all. It compiled right away. Believe it or not, it compiled right away. So what the fuck? Do we even use like and b? Yeah, we also use and b and or b. Yeah. So all of that seems to be working. Yeah, so as you can see, we can just keep piling things on top, but I do not guarantee if it's gonna work like first try. So no guarantee for that is gonna be given. We'll see how it goes. So after that, we computed the amount of neighbors, right? So we computed the amount of neighbors, and now we need to get the value. We'll need to get the value of the current cell. So we need to compute this thing. So it's going to be cell pointer, boards base plus cast pointer board size multiplied by board current, plus row multiplied by board columns plus column. There we go. And then I'm going to save it to the cell. Cell is going to be equal to load pointer u8 from the cell pointer. Right. And again, there are two situations in here. When cell is dead, right? So it's going to be equal like less than 1, that means it's dead, right? So this is a dead cell, and otherwise it's going to be alive. So here's the alive cell. So let me see if this entire thing compiles. Boards less cast u8. Okay, seems to be compiling. Cool. So if it's dead, I don't remember the rules of the game of life. Game of life. Wikipedia conveys game of life. Also, let me actually put that into the description. Game of life. There we go. Conveys game of life. Okay. So if it's dead, any live cell, any dead cell with 3 live neighbors becomes a live cell. Okay. If it's dead and amount of neighbors is equal exactly 3, we don't have exactly equal. All right. So I want to try something. Let me actually quickly try to add the equals, right? So let's actually cut out the process of me adding new equals operator, because you've seen me doing that multiple times. So I think we can actually make a shortcut. So yeah, see you in a second, and we're gonna have this equals operator in here. Okay, so I made a pretty cool shortcut. So I managed to reuse the same token that you use for assignment. You know how I managed to do that? This is because the assignment is a statement and not expression. So it was just, okay, it was easier to implement it this way, all right? So basically equals in the context of statements, statement means assignment, but in the context of expression means equals. I'm gonna fix that later. I know that it's horrible. But it is what it is. It was just easier to do this way. All right, so maybe I'm gonna put something in here. Yeah, as you can see, I associated the binary operation equals with the token kind equals. Right. So introduce a separate token for equality. Using the same tokens for assignment and equality is very confusing. Okay, so I put it to do in here, but for now, right, depending on the context, right, this thing is going to be different things. In the context of a statement, it means assignment. In the context of expression, it means equality. All right, so, and as you can see, this entire thing actually compiles, so everything's fine. So if this thing is equal to 3, right, if it equals to 3, we need to assign the new cell in the next state to alive. Otherwise, we have to assign it to dead. So we need a pointer to the next state. So we're gonna just do that and just gonna use the next board in here, and I'm gonna just store ptr u8 cell ptr cast u8 1. So this thing becomes alive. Otherwise, it becomes dead. There we go. Cool. So this is next, this is that, and if you are alive, any live cell with 2 or 3 live neighbors survives. All right, so we are alive, neighbors equal 2 or neighbors equal 3, this thing becomes alive. Otherwise, this thing becomes dead. And I hope I didn't make any mistake in here. Right, if you are dead, right, we might as well actually make it equal 0, right, just make it equal 0. If you're dead and you have 3 neighbors, you become alive in the next state, you see? So this is the pointer to the next state. If otherwise you have, like, you become dead. 2 or 3 alive, you stay alive, and then you become dead. All right, so it's a little bit complicated, but it seems to be reasonable. Okay, after that we increment that, and after we're done doing all of that, the current board becomes the next board, right? So the next board becomes the current one. And that's how we keep flip-flopping between these things. Does it even compile? This is sus. Oh, neighbors. Yeah, I thought it's gonna fail in here, but neighbors is actually I64. So that's why I managed to compare this entire thing. So I don't have to do this kind of thing because the literal right now is already I64, so I don't need to cast anything to anything. Funny enough, if I try to cast this to I64, it's gonna say something funny. Yeah, I cannot convert value of type I64 to I64. Maybe I should just add a condition saying that if you're trying to convert value to itself, just allow that to happen. But I mean, I couldn't bother to do it right now. All right. Theoretically, this should be it. Theoretically, but I'm hella terrified to try it out, because if it doesn't work, I have no idea how we're gonna troubleshoot that. And it may not work because we had to implement a couple of operations and I actually never tested those operations, so it's gonna be hella fun. All right, so again, we can test how the board is printed. So let me just try to run this entire thing, and as you can see, here is the state of the board, and we have a glider in there, and I'm gonna just try to run it with the next board and see if it finishes. Okay, so the next board code, this entire code terminates, at least, which is already good, but does it even do anything? Let's actually add some sort of like a side effect, right? Just to see that it's doing something, that this code is actually executed. Okay, so it iterated this amount of rows and everything is like has terminated, which is nice. Okay, this is a good sign. So now let's try to print the next state. And it's dead completely. Nice. I wonder why. I wonder why. Right, it actually set all of them to 0, which is fine, which is fun. So again, I have no idea why. I have no idea why. So maybe we're gonna try to like another this trick one more time. I'm gonna just pause, try to understand what the fuck is going on, and then I'm gonna unpause and explain what exactly is going, what exactly was the problem. So we'll see how it goes. So see you in a snap. Okay, so this is absolutely fucking dumb. So this is something that could have been easily prevented if we had for loops over ranges or something like that. Right, so guess what's the problem? Ah! Okay, I'm sorry if it was too loud, but yeah, so now this is literally the next state of the glider. It fucking works. My god. Mein god. Okay, so let's actually add more of these things in here. So this is going to be the next board. I'm not sure. Let's actually put it like this. It's going to be like that. And the next state is that. I want to keep piling until it repeats itself. Right. And it repeated itself. Look. Game of life. But unfortunately, it's not particularly interactive. You know what I mean? It's not particularly interactive. It would be kind of cool if it actually sort of did that in real time. We can put it under like a loop, if you know what I mean. We can put it under loop. So it's going to be print board while true, right? So it's going to be something like this. And I don't want to run it in Emacs because it's kind of dangerous. So because Emacs is a very slow terminal emulator. So yeah, it was too fast. Unfortunately, it was too fast. So I could probably slow it down a little bit, but I have no idea how to slow it down because we don't have a sleep in our virtual machine, right? So maybe we can put some empty loops in there. But in any case, I think we managed to implement that. So let me see. So we can have like limited amount of iterations. So let's introduce var i64 and I is equal to 0 initially, less than 10. And do we want to write something like this in here? Yeah, there we go. And if I try to run this entire thing, I forgot to increment. We definitely need for loops. Yeah, doing that with while loops is absolutely horrible, but yeah. So here is the game of life, and we have a moving glider. And again, so we can try to compile it down to a native code. So let's quickly do that. So it's going to be build toolchain bang list. And I'm gonna grab the NASM Linux x86-64 and the example is going to be goal bang example. Do we have goal asm now? It's pretty big, not gonna lie. Yeah, almost 500 instructions, BM instructions if to be precise. NASM f64. And let's try to compile it down to O, and then let's try to link this entire thing. Goal O, and we have a native executable, and if I try to run this native executable, it is working game of life, more or less, right? That's pretty cool. So let's make a pull request, I suppose. So what do we have in here? We added a bunch of operators, and or in equal. Okay. Add and or and equal operators to bang, and implement game of life in bang. And I'm gonna push that right into the repo. So, and let's create a pull request for this thing. So I think it's already, yeah, it's already pushed. And I guess that's it for today. That's it for today, boys and girls. Thanks everyone who's watching me right now. I really appreciate it. Have a good one, and I see you all tomorrow. Tomorrow is gonna be Friday, and I'm not sure what we're gonna do tomorrow. Because we usually do a random one-off stream on Friday. But I kind of want to continue developing this language because there's a lot of things that we need to implement for this language. But at the same time, I don't want to be stuck with the same topic over and over again. So I use Fridays as an opportunity to discover something new, to try like new things and stuff like that. So maybe I should not skip a Friday. I should just like do a random topic, because I discovered a lot of interesting things that inspired me in like at Fridays usually. So yeah. Hopefully this stream was interesting. I hope a lot of cuts didn't ruin the stream too much, because I want it to be like sort of like a seamless experience. But some things are not just really interesting to watch, like me making a cup of tea or me struggling to understand where the fuck I forgot to put a character or something. So yeah, in any case, thanks everyone for watching. Love you all. Mwah.